Gilbert Lewis was a professor at the University of California, Berkeley in the early 20th century. Lewis invented the word photon. He was the first person to isolate pure deuterium oxide. And over 100 years ago, in 1916, Lewis published a paper where he proposed the idea that covalent bonds, formed by the sharing of electron pairs, were the driving force that held atoms together in molecules. In that paper, Lewis laid the groundwork for one of our most transformative and enduring models of chemical bonding and reactivity, one that we're still teaching and using more than 100 years later in the form of Lewis structures. For that achievement, Lewis was nominated for the Nobel Prize 41 times. But he never won because he was a real big jerk and he kept picking rivalries with the other members of the Nobel Prize Committee. In 1946, at the age of 70, Lewis was found dead at the lab bench, possibly after he deliberately exposed himself to hydrogen cyanide. We've already had some practice drawing Lewis structures and using those structures to help understand patterns of bond lengths and bond strengths. But it turns out that Lewis structures have some pretty severe limitations, and they don't always describe molecules as well as we would like. Look, this bonding model is so old, it predates the National Hockey League. It's not going to be perfect. Lewis structures assume that a given pair of electrons can only exist on one specific atom, or in a bond between two specific atoms. But electrons don't actually do that. In real molecules, the electrons are waves that can span the entire molecule. That behavior isn't captured by a Lewis structure, and so one Lewis structure alone, with just one possible arrangement of electrons, won't always correctly predict the observed molecular properties. Can we better represent the delocalization of electrons in a Lewis structure? Do we even need to? If we do, how do we represent the change in position of the electron pairs? We can answer all of these questions, and we can improve the Lewis model of bonding by using resonance structures. The concept of resonance allows us to imagine that electron pairs might be distributed across multiple atoms or multiple bonds. Lewis structures of the same molecule that depict the electron pairs in different positions are called resonance structures. This is a powerful extension of the Lewis model because it allows us to better understand the patterns of bond lengths and bond strengths in molecules where electron delocalization plays a role. To represent the relationship among the resonance structures, we're going to learn a new way to think about the movement and position of electrons in a structure, the curved arrow formalism. But before discussing resonance, let's quickly review Lewis structures. Grab your pen. Recall how we go about drawing a Lewis structure. First, count the total number of valence electrons in all the atoms, and then start connecting the atoms using bonds, 2 electrons for each bond. Hydrogen and more electronegative atoms go around the outside. Any remaining electrons should be placed initially as lone pairs on the outer atoms, except for hydrogen. Nope, no lone pairs on those H's. And then the electrons left are placed as lone pairs in the center. Check for the octets. Okay, that looks good for ammonia. And all the atoms have 0 formal charge, so that's good too. For azide, remember to add an extra electron to the total for the negative charge, but then follow the same rules. First, single bonds connecting the atoms, then lone pairs around the outer atoms. This time we don't have an octet at the center, so we need to shift some of the lone pairs and turn them into bond pairs. Do that twice. Now all the atoms have octets, and we do have some formal charges, but none of them is very large, and there's no way to avoid them without violating the octet rule. So now the azide is done too. Most of the time, there will be only one choice about how to arrange the electron pairs, and so only one valid Lewis structure. But that's not always true. Sometimes you have to move electron pairs in order to satisfy the octet rule, or in an attempt to minimize the formal charges, but there's more than one way to do it, and that can lead to more than one possible Lewis structure. How do you know which one is correct? Well, this leads to a very important issue. If you look at just one of the structures that we drew for ozone, it has 2 different kinds of OO bond. One is a single bond and one is a double. Now, if this is a good model, it should accurately predict the bond lengths in ozone. And it suggests that one bond is a double bond, like in dioxygen, and one bond is a single bond, like in hydrogen peroxide. But that's not actually what we observe. Ozone molecules don't have a short bond and a long bond. Ozone molecules have 2 identical bond lengths that are right in between what a single and a double bond should look like. In a real ozone molecule, the bond lengths are exactly equal, and they're intermediate between a single bond and a double bond. We can explain that using the concept of resonance. Each of these individual representations of ozone is called a resonance form or a resonance structure. Neither of them is correct by itself. But we can imagine a superposition of these two different resonance forms, a single structure that isn't either one of them alone, but instead is a sort of average of their features blended together. That superposition is represented using this double-headed arrow called the resonance arrow, and the resulting combined structure is called a resonance hybrid. In this case, the hybrid has 3 bond pairs shared equally across the 2 OO connections. That means that the OO bond order for each interaction is 1.5. The 2 bonds are equal, and they are both in between a single and a double. That's just like the experimental observation. This resonance hybrid, which you could draw using a dashed line to represent the half bonds, better explains the observed properties of ozone than either of the individual resonance forms alone. So let's look more closely about what actually happens to the electron pairs when we change from one resonance form to another. In this ozone example, we need to change the position of 2 pairs of electrons. This lone pair on the O must shift in to become a bond pair, and this bond pair on the other side must shift out to become a lone pair. We represent these shifts using curved arrows to indicate the apparent movement of electron pairs. Each arrow starts on either a bond or lone pair and then shows you where those electrons will appear in the new resonance form by directing that pair either to a new atom to become a new lone pair or to a neighboring bond to become a new bond pair. So here are some key points to remember about drawing these resonance forms and about using the curved arrows. Different resonance forms will not change the position of the atoms. They don't move and their connectivity can't change. Only the electrons can change position. All resonance forms have the same total number of electrons, so they must have the same overall formal charge. But the individual formal charges, again, they might move around because you are changing the electron positions. Every curved arrow starts at an existing electron pair, maybe a lone pair, maybe a bond pair, and directs it to a neighboring atom or bond, which will be that electron pair's new position in the new resonance form. Now you practice. Here's one possible resonance form of the formate anion, with curved arrows showing you how the electron pairs will have changed positions in a different resonance structure. In that new resonance form, what will the formal charges be on the carbon atom and the top oxygen atom? 0 on both, just like in this resonance form. -1 on carbon and 0 on oxygen. 0 on carbon and -1 on oxygen. +1 on carbon and -1 on oxygen. No, pay attention to what the arrows are telling you and redraw the bonds and lone pairs accordingly. Nope, there's a second arrow leading from the CO double bond to the oxygen atom. How many lone pairs will it have in the new resonance form? That's right. A lone pair on the negative oxygen atom becomes a new carbon-oxygen bond pair, so that oxygen loses its charge. On the other hand, the other oxygen gains an extra lone pair, so the -1 formal charge appears on that second O. So what this indicates is a total of 3 bond pairs distributed equally over the 2 carbon-oxygen interactions. That leads to an average CO bond order of 1.5 in the resonance hybrid. Both CO bonds are identical. Try another example. Here are 2 possible resonance forms of the thiocyanate anion. Where must you draw arrows in the structure at left in order to show how the electrons have moved to form the structure at right? No, this arrow will move one of the carbon-nitrogen bonds to a carbon-sulfur bond, so we'll get the correct double bonds between C and N and C and S. But this arrow doesn't put the lone pairs where we need them. These arrows will result in the correct pattern of bond pairs and lone pairs, but one of the arrows is sending a lone pair on the sulfur to another atom 2 bonds away. In resonance forms, curved arrows can only move electron pairs to a neighboring atom or bond. Not quite. One of these arrows is directing a sulfur lone pair onto the carbon atom, which would produce a lone pair on that atom in the other resonance form. We need a sulfur-carbon double bond, not a carbon lone pair. That's right. This will give us 2 lone pairs on the sulfur, we lose 1. A sulfur-carbon double bond, we gain 1. A carbon-nitrogen double bond, We lose a bond there. And 2 lone pairs on the nitrogen. We gain 1. But here's the most important thing to remember. This apparent process of moving the electrons from place to place does not actually happen. We are not using curved arrows to represent a real movement of electrons within these structures. We have to invoke resonance forms to give the false appearance of electrons changing position, because Lewis structures are dumb and they think electrons can only be in one place at a time. Real electrons in real molecules don't have to move from one place to another. They're already everywhere. Electrons are actually delocalized, but we can't show that with a single Lewis structure, so we have to use resonance. We get a model closer to the true structure in the resonance hybrid. Now, not all Lewis structures require resonance forms. So how do we know when we need to worry about them? If you ever find yourself making an arbitrary choice about how to arrange the electron pairs in a Lewis structure because there's more than one valid arrangement, then all of those valid electron pair arrangements may be important resonance structures that will contribute to the resonance hybrid. If you have bonds in a Lewis structure where the second bond to one atom could be delocalized over other equivalent atoms instead, you should consider those other resonance forms. If an atom with a multiple bond is connected by a single bond to an atom with a lone pair, it may be possible to rearrange the lone pair and the bond pair electrons to form a new resonance form. You'll learn to spot these patterns with practice. But the best guide is this. You draw resonance structures when the real properties of the real molecule tell you you have to, because the single Lewis structure that you have isn't describing it properly. This is a model, and it's only as good as its ability to help you understand the thing it's modeling. So compare your model structure to the real structure. And if they don't match, your model needs to be fixed. Resonance forms are a good way to do that. So, today we learned about resonance structures, an extension of Lewis theory that lets us draw the electron pairs in different positions. We learned how to tell when we might need to invoke resonance structures and how they can help us better explain the properties of molecules where electrons are delocalized. We also learned about curved arrows, which we use to depict the apparent change in position of those electrons. In your next class, you'll spend some time applying these ideas to a much wider range of molecules, including bonding systems found in some biological structures like proteins. This model is so old, it predates women's right to vote in Canada. This model is so old, it predates the 40-hour work week. This model is so old, it predates the first commercial recording of jazz music. This model is so old, it predates audio and film. This model is so old, it predates Agatha Christie's first novel. This model is so old, it predates the discovery of hafnium and rhenium. This model is so old, it predates the Soviet Union, Yugoslavia, and Czechoslovakia. Those countries don't even exist anymore. This model is so old, it predates the Battle of Vimy Ridge and the Halifax explosion, a part of our heritage. This model is so old, it's older than John F. Kennedy, Ella Fitzgerald, and Arthur C. Clarke, who are all dead. This model is so old, it almost predates the founding of UBC.